Okay, so good morning, everyone. Thank you for being here. I'm Alexandre Gazet, and with Fabien Perigaud, we are going to present you the work we've done on iLO 4 and iLO 5 BMC. We've done this work with Geoffrey Xani, who could not be there today. What we are going to present you today is kind of a summary of all the work we've done on this subject, on something like 1 year, not full-time, obviously, but still it's a significant effort. So, to introduce the subject of BMC, BMC stands for Baseboard Management Controller, and it's just a feature that allows you to manage your server remotely. So you can, for example, check the health of your hardware, of the operating system as well, check temperature, things like that, and sometimes, of course, we can get some remote console and this kind of stuff. Something to keep in mind is that BMC, actually, it's implemented as an hardware feature. You have a dedicated chip on the motherboard of your server. On the left, you have iLO 4, on the right, iLO 5 chip. So it's directly integrated on the motherboard. We are going to talk about iLO, Integrated Lights Out Study. It's a BMC technology from Hewlett-Packard, HPE. You can find the same, exact same technology from different vendors. For example, Dell has iDRAC. You can find Supermicro, Lenovo IMM, and so on. Yeah, it's very important to keep in mind that it's really a standalone system running alongside your main CPUs and your main operating system. For iLO chip, it has a dedicated ARM processor, dedicated non-flash chip, dedicated RAM, also dedicated network interface. That's very important. And of course, there is a full operating system and application image that runs as soon as your server is plugged in, as soon as it is powered off. Even if your main operating system, Linux or Windows, is shut down, the iLO will be running. And something important we thought at the end of this talk is there is a silicon root of trust introduced with iLO 5 systems. Why did we start this study at first? For years, actually, we were kind of frustrated because when we found iLO systems during pen tests or various engagements, we could not do much about it, actually. Even if we managed some way to get iLO credentials, we could access the system, but what we could do eventually was to reboot the system remotely with custom ISO, with another system, and try to access the hard drive if it was not encrypted. But of course, it is fucking noisy, so you won't do this really in production. And there was not much things we could do. There was known weaknesses on IPME protocol, the famous Cipher 0 on V1 of the protocol, which basically is a hot bypass. And there's still the kind of weakness on IPME V2, which sends you a hash of the password as a challenge when you try to attempt with a server. So that was the state of the study around these systems when we started. And yeah, it was kind of unsatisfying. We wanted to know if, for example, if we could reach the host, the main server, from a compromised iLO, but also on the other side, if we can try to attack what was the attack surface from the host to attack the iLO systems. That's why we started what we call a deep dive evaluation. We invest some important amount of time, more than 200 days for the three of us, to build a detailed cartography of the attack surface, both from the host side and from the administration side. We found many vulnerabilities that we will talk about during this slide, and something important, we identify a new exploitation technique using DMA access from the iLO system to attack the host system and the other way around. Of course, we had to develop some tooling to be able to manipulate firmware, understand them, and reverse engineering them, of course. There has been lots of light put on BMC subject in 2018. The team from Eclipsium worked on Supermicro, guys from Humanity on iDRAC, and of course we have been publishing on iLO systems. So interesting to see that the subject come, all these subjects come at the same time. So now Fabien will talk to you about the first step we took to attack the iLO.
Hi everyone. This study was performed in 3 parts, and I will start telling you about the two first parts. So first one was how can we attack the host operating system from the iLO, and the second one was to check if we can backdoor an iLO system. So how did we start this study? We started by recovering a firmware update for iLO. We studied the file format to understand how it was structured. We extracted all the components of the firmware. So there's a bootloader, a kernel, and a userland image containing various userland processes, also various signatures. We started to analyze the kernel. So the operating system running on iLO is Integrity, which is a real-time operating system developed by Green Hills. Finally, we understood the memory layout of the different userland tasks. So a task in a real-time operating system is a kind of process on a normal operating system. And we developed various loaders for IDA Pro, so you can now just load an iLO task directly in IDA to study it. All the tooling we developed is now available on the Airbus GitHub repository that you can see on the screen. So you can reproduce all this work at home with your own iLO. After understanding how the firmware was structured, we could start to analyze the attack surface. So there are 49 userland tasks running on iLO, and some exposed endpoints on the network interface. So there's an SSH server, a web server, some REST APIs, the iLO virtual media port, which is a port used to simulate the presence of a CD-ROM on the server, IPMI, SNMP, UPnP, etc. And some of these components are fully homemade. For example, the web server and the SSH server are fully developed by HPE and do not rely on open source bricks. So this is quite interesting, and we started to look at the web server to see if we can find some vulnerabilities in it. And indeed, we found one. This is a CVE we found in 2017. It is a pre-authentication, remote code execution, and authentication bypass on the web server component. It has already been fixed by HPE in version 2.53 of HPE iLO 4, sorry. How can it be exploited? Well, if an attacker has a foothold in the LAN or in the DMZ and found an iLO 4 system with a web server running, it can just exploit it to gain remote code execution on the iLO, and then try to pivot to compromise maybe other iLOs, or to try to rebound on the host operating system. We will see later how it can be done. For some technical details, it's just a simple buffer overflow triggerable pre-authentication. It's just a buffer overflow in the HTTP connection header. So you just send a connection header with more than 16 characters and you trigger the buffer overflow. For the technical details, you can overflow a static buffer in the HTTPS connection object. And with this overflow, you can either overwrite a Boolean we call local connection, and if you overwrite this Boolean, you can simply bypass authentication, and you don't crash the web server, etc. You just have the authentication bypass, or you can try to overwrite the virtual table of the object to gain remote code execution, which is made easier by the fact that there's no ASLR or NX on iLO 4. So when we gain remote code execution on iLO, we wanted to see how we can rebound on the host. So we started to reverse another task, which is the channel interface, which is a task to communicate with the host. And we found that there were mentions of WHEA records parsing, which is a Windows hardware error architecture. So it means that the chief was able to reach the host operating system RAM. So we studied how it can be done, and we reproduced it in a shellcode. And by exploiting the vulnerability in the web server, we were able to access the host main memory. You can find more details on all this stuff on the repository. So a quick demo to illustrate this. We plan to compromise an up-to-date Linux running on the HP server. So we will use the vulnerability in the web server to access the host memory. We will dump the Linux kernel in memory. We will do some recon to find some interesting symbols in it, and then replace some unused function in the kernel, hijack the syscall table to run a shellcode, and then pop a shell on the Linux. So let's see how we can do it. So here on the left, you have the attacker, and on the right, this is the Linux server running on an HP server. So as you can see, there's nothing weird listening on the network for now, and the attacker tries to connect to a specific port and can't. So first, we will dump the memory of the Linux kernel. So we will dump approximately 16 megabytes of memory to have the whole kernel image, so we can find some symbols in it. So well, it takes some time. So now that we have the dump, we will search for some symbols. For example, some code we can overwrite, which is not used in the Linux kernel. So we take the serial port handling code. We will then rewrite this code with one of our shellcodes. So as you can see, the simple is quite simple. We just want to execute netcat listening on a port popping a bin bash. And finally, we will patch the syscall table to patch the read syscall entry, so that as soon as read is called, our shellcode is executed. And if we have a look at the server now, there's something listening on the port. And of course, the attacker can connect and gain the root shell on the server. So now that we've proved that we have access we can gain access to the host from iLO, we wanted to go further. One other thing interesting to note, I was telling you earlier that the web server and the SSH server were homemade by HP. So, well, a friend of us found another vulnerability, this time in the SSH server. So it's Nikolaios from the French National Security Agency. This time it's a post-authentication vulnerability, but well, as soon as you get credentials on the iLO, you can connect to the SSH and use this vulnerability to do exactly the same than we did earlier. This is a format string vulnerability, so format string are still a thing today. So the next step, we wanted to see if we were able to backdoor the iLO firmware to gain persistence on the system. So looking around, we found a module called SPI, which exposed SPI service giving direct primitives to the SPI flash hosting the iLO firmware. So what we did was simply in our shellcode invoke the SPI service to directly write backdoor firmware on the flash. So by doing this, we bypass all the checks which are normally performed by iLO when you submit a firmware. However, there is some integrity check when the iLO boots. So as you can see on the schema, when the iLO is reseated, the bootloader starts. It then checks integrity of the kernel, then decompress it and load it. Then the kernel will check integrity of the userland part and decompress and load it. But well, nobody checks the bootloader. So this is a problem because we can take a normal firmware, extract all the part of the firmware. We can patch the bootloader to remove the integrity check of the kernel. We can then patch the kernel to remove the integrity check of the userland. And then you can simply inject a backdoor in the userland, repack all the firmware, flash it using our vulnerability, and then we have a backdoor in the iLO. So for the proof of concept, the backdoor we wrote was a specific handler in the web server part. So we added a get handler on the web server to gain direct access to the host memory in a read and write. So as you can see, for example, we used here the backdoor on a server running a Windows 10 operating system, and we asked him to jump the memory at 10,000, and we can see we have the Windows 10 bootloader, for example. Then we wondered what we can do with this backdoor. So we started to develop a service to connect our backdoor with the PCI Leech tool. I don't know if you know it, but PCI Leech is a tool you can use with a hardware or memory acquisition software memory acquisition system to perform some actions on the systems. For example, you can unlock a Windows session, you can insert directly a kernel module in the operating system. So we developed a connector with PCI Leech, so we can use PCI Leech with a compromised HPE iLO to perform all the tasks it can perform. So here, for example, is the use of PCI Leech with our backdoor on a Linux system to inject a custom kernel module. So while it takes only 2 minutes for PCI Leech to retrieve the Linux kernel and inject its module. And finally, for the light side of the force, we played a bit with the NotPetya malware. So NotPetya is a ransomware which appeared in 2017. The fun thing is that it rewrites the MBR of computers so that when you reboot your computer, the custom MBR runs and it will encrypt all your disk with a randomly generated key. But our friend Adrien Guinet from Quarks Lab found that the encryption key will stay in RAM after the reboot of the computer. So using our DMA access with iLO, we can simply recover this key from RAM. We can patch the NotPetya MBR to make it decrypt itself on the next boot. So this is what we did. So here is the screen of NotPetya. It asks you a decryption key if you pay the ransom, and well, by using iLO, we can just re-inject the key dynamically and ask him to decrypt itself. So well, this is a fun proof of concept of what can be done with this backdoor. And well, we published a white paper about this yesterday, so it's also available on the GitHub repository. So this is all for the previous work. Now we will focus on the third part of our study, which was studying the attack surface from the host operating system to the BMC. And finally, we will have a look at the new iLO version, which is iLO 5. First recap of the iLO architecture. So here is the image of an HP server. On one side, you have the main CPU, so usually an Intel CPU running a classical operating system. So here it's Linux with all the userland processes. And on the other side, you have the iLO CPU, which is an ARM CPU running the integrity operating system with various userland stacks. And the communication between both worlds is done over PCI Link. Well, all these parts will apply for iLO 4, but most of it will be also valid for iLO 5 with some slight changes. So, to study how the communication was working between iLO and the main operating system, we started to look at the available tooling to make normal communication. So, in the Linux kernel, there's a driver called HPE iLO, which exposes some character devices to communicate with the iLO. It requires root privileges to use these devices. And HPE also publishes some proprietary tools to modify the configuration of the iLO or to flash a new firmware on the iLO directly from the Linux host. So this was a good base to start studying how the communication worked. So from the operating system point of view, iLO is seen as a PCI device. So you can see by doing an LSPCI, you have an integrated Lighthood standard management processor device appearing. And if you have a look at the physical memory map of your system, you can see that there are several ranges of memory which are reserved by the HPE iLO driver. In these shared memory segments, some communication channels are set up by the driver. So there can be 8 to 24 channels, and each channel is exposed as a device in the dev HPE iLO file system. And each channel has a quite simple FIFO structure. On the iLO side, the task in charge of handling all the communication is called chief. If you remember, it was a task in which we found the DMA feature on iLO. So the chief task simply waits for messages from the host and then just dispatch the command it received to the correct command handler. And it can also dispatch certain messages to other tasks on the system. The message format is quite simple. There's a size, a command ID, a destination ID, which means which task should handle the command, and then a data buffer. And what's interesting is that by default there's no authentication on this channel. So that means that as soon as you have administrative privilege on the host operating system, you can talk to the iLO and you can configure the iLO without any authentication. So about the commands you can send to the iLO, there are more than 100 commands which are handled by chief. So, for example, you can get the iLO network configuration and you can modify it, etc. But there are also some dangerous commands. For example, command 70 allows you to dump the iLO EEPROM. The EEPROM contains the factory settings of the iLO, including the default administrator password in clear. And it's quite interesting because usually this password is never changed by the administrators. They prefer to create a new administrator account with new passwords. The main reason is that the default administrator password is written on a sticker on the server. So, well, if you forgot the password of any other account, you still have this one to use. So it can be useful. There are other commands. For example, commands 50 and 52 are commands to update the firmware of the iLO. And another command is to create a new account of the iLO. So from the host operating system, you can create a new administrator account on the iLO without any kind of authentication. Well, a quick example on how you can communicate with the iLO with 6 lines of Python. So this example is the command 70 I showed earlier to dump the EEPROM. So you can see in the EEPROM dump you have the administrator username and the default password in clear text. We then focused on the command handling the firmware update. Why did we choose this one? Because it involves complex file format parsing. The firmware update task have to dump or to handle the firmware file parsing. There are various signature checks, so there might be an error somewhere. And if we find a vulnerability in the firmware update mechanism, we might be able to also to install a backdoor firmware on the server. And another point of interest is that this feature is accessible from both the host and the web server. So from the web server, you can also upload a new firmware on the iLO, which is then updated. So let's have a look to the firmware update workflow. So first of all, you send a new firmware from the host or from the HTTP web server. Then this firmware is sent to a specific task called Fume for firmware update module, maybe. The Fume task will perform a first validation on the firmware file and its signatures. It will then ask the integrity kernel for additional validations. And finally, if everything goes well, it will send the new firmware to the SPI service, which will write it effectively on the SPI flash. A quick recap on the file format. So when you the file you provide to the iLO has a small header called the fingerprint, which has a signature, the signature of the whole HPE image, which is the actual firmware. And this header will be passed line by line by the Fume task, and it will try to retrieve the hash and signature elements, then compute the hash of the whole HPE image block, and checks the signature using an hard-coded HPE public key. Then a quick recap of the HPE image format. So this IP image contains the actual bootloader, kernel, and userland images. So as I said before, kernel and userland are compressed and signed, but the bootloader is uncompressed and unsigned. And during the boot process, bootloader asks code to load and verify the kernel, then the kernel asks code to load and verify userland. but your bootloader is never verified by the boot process. And this is what the kernel will check. If you remember the fourth. Sorry. Well, if you remember the first part here, the Fume will ask the kernel to do some additional validations, and these validation which will be done by the kernel. So the kernel will expose a specific resource to userland task with 10 different commands handlers. And Fume will use the command number 2 to ask the kernel to verify integrity of the kernel and userland images. So the kernel will decrypt the embedded signatures, will compute the hashes and compare them to the decrypted signatures, and it will try to decompress the images if they are compressed to see if the compression is valid. And one important thing also there is that there's a command which can be used to provide a new key to the kernel for verifying signatures, which means that if we have a code execution in Fume, we can just ask the kernel to verify the firmware with a key we control. So to summarize the signatures verification step in the firmware update, so first the whole HPE image is verified in the Fume task, then the userland and kernel images are verified by the kernel, and finally during the boot process of the iLO, the kernel and userland will be also verified. And of course, on iLO 4, the bootloader is not signed. So we saw earlier that with a single vulnerability in userland, we can write directly bad firmware asking directly the SPI service. Then the bootloader can be patched to avoid kernel signature. Kernel can be patched to avoid userland signature, and then we can have a backdoor in a userland task. So now let's check in details how the Fume will do the parsing of the fingerprint header. So as I said earlier, it will read this header line by line to find the hash and signature elements. But we can see somewhere it will call a readline function providing a fixed size buffer on the stack and specifying no size. So that's not always a good idea. What could go wrong here? And as we can see, the line which is read in the header is directly copied in the fixed size buffer without any side check. So there's that's a trivial buffer overflow which is of course exploitable to bypass the firmware validation. So we managed to exploit it. We first wanted to exploit it without code execution because it would be easier. So we thought that we could simply redirect code execution to just bypass the signature validation and then let the process continue to effectively flash the firmware. But there was this second check in the kernel we couldn't bypass this way. So in fact, we had to do code execution, which was made easier by the fact that there's no ASLR, no NX in iLO. So we could simply write a shellcode in our firmware file, which is sent to the service. And as this firmware file is loaded on a fixed, at a fixed address in memory, we can simply jump on the shellcode, and the shellcode will just ask the SPI service to effectively write the firmware on the SPI flash. This vulnerability has been reported to HPE in May 2018. It impacts both iLO 4 and 5, and well, patches has been made available by HPE in May and June 2018. What's fun is that it has been called a remote or local code execution because you can exploit it either from the host by flashing a vulnerable firmware on iLO or directly from the web server interface. So now that you can see how secure iLO is, you might want to disable it on your HP server. So, well, one good thing is that if you go to the in the BIOS of your HP server, there's something you can check to disable iLO. When you reboot the server, you can see it tells iLO 4 is disabled. You can see iLO 4 IP disabled. So, okay, I might be safe. But, well, if you try to communicate with the iLO from your Linux, you can still communicate with it, which means that iLO is still running, and it can still be joined by the main operating system. The iLO disable feature is just that it's not reachable from the network anymore, but it can still be reached by the host operating system, which means that you can still be backdoored by an iLO vulnerability. So now what? We already proved that the firmware backdooring was possible. In the previous work, we developed a backdoor in the web server to install a specific handler to access the host memory. And now we are able to do it from the host, even if iLO is disabled. So, well, as soon as we can compromise a host operating system running on an HP server, we are able to set up a persistent backdoor in the iLO. So now let's see the new work we did on iLO 5.
Yes. So iLO 5 was introduced in mid-2017. It was a new generation of server, Gen 10, and it's of course, when it goes out, we wanted to have a look at it and to get an idea about the evolution of the exposed attack surface from iLO 4. Really, it was not a vulnerability research campaign. We wanted to understand what was new on the system, and there was a key feature in it that was really appealing to us. It was a silicon root of trust. So introduced with a new chip, hardware root of trust within. So we bought a new server, a cheap one, and we started to look at what we got. So we identified quickly the two flash for system RAM and iLO RAM, the RAM also, but we had no luck trying to identify the SOC that is used by the iLO chip. We knew it's an ARM chip, Cortex A9, but we had no information about what was its cryptographic capabilities in particular. We suppose the board design has been made by Wistron Corporation due to some documents we found looking for markings on the motherboard. So again, we started doing a firmware analysis to understand its format. So the firmware is 32 megabytes. It's also wrapped into an HPE image sign container. It contains a boot block, the last 10,000 bytes of the firmware. And then we have a list of modules. Each of them is present, there are two copies of each of these modules for fault tolerance when writing in the flash. Each module is described by a header and is also signed, both the code of the module and most of its header. If we look at one of these header, we can find some very specific elements. There's one magic at the beginning, one at the end, a header type, which tells you, for example, if it's iLO kernel, iLO userland, or maybe first stage bootloader or second stage bootloader. We can find CRC for both the header and the image. At the end, you can see we can have up to 2 signatures. And we also found some very important parameters that we will talk about just after, which are cryptoparam index. So once we understand how the header is composed, we can simply dump and list, of course, all the modules that are present within a firmware. We have various bootloaders and also kernel and userland of the systems. So just to give you a preview of how the boot chain is made, so we have the ASIC, the chip, with a boot ROM that will load first stage bootloader, which is Secure Microboot 1, SMB1, and a second stage bootloader, NEBA 9, and then iLO 5 kernel, and then the userland at the end. So we started to investigate and looked at how this secure boot is implemented. So this is our guess about what the boot ROM performs as action. We suppose it loads all the firmware in the upper memory addresses, and it will, from then, it will check the signature present within the SMB0 header. It allows to check the signature of the first 8,000 bytes. Then it will use the signature from SMB1 header to check the integrity of the first 5,000 bytes. And if everything is good, it will trigger the harm reset vector, and the processor will start executing the secure microboot code. So first stage bootloader. So we have a first stage bootloader, SMB secure microboot. Of course, it's very minimalistic. It only performs some CPU initialization actions, like instruction data caches and things like that. Interestingly, trust zone is not used on this ARM CPU. Also, it will access some non-volatile memory. Something interesting also, yes, it exposes an API. We will talk more about it just after. And at the end, it will load the second stage bootloader, which is NEBA 9 in the nominal behavior. So How is the signature checked? We can, like we said, you can have up to 2 signatures stored in the header. So it's a simple RSA signature for key. And in the data of the first stage bootloader, we have like a flat array of big num. The first one is the exponent, and then we have an array of 6 public keys that can be used to check the integrity of the next stage. So quite simple. So when Secure Microboot wants to check the integrity of the next stage bootloader NEBA 9, it will pick the value of index, for example, index 1, get the matching public key, decrypt the hash from the signature, and then verify it by computing the hash of the body of the NEBA 9. And if everything is good, it will load it, it will execute it and pass execution to it. When we reverse engineering this process, we found that actually there are 4 bytes that are not included within the computation of the checksum, the hash of the module, 4 bytes from the header of the module. And actually, these 4 bytes are for the 2 fields, index 1 and index 2, that allow to select which public key is used to select which public key selected. Sorry. Our guess is that, again, this feature can be used for post and cross signature by 2 different entities. We have not observed some use of it in the firmware we collected, but it could be an explanation for this. At that point, we don't see any exploitable way with or something we could do with that weird things, but we had that in mind still. So now we are in Secure Microboot. Secure Microboot loads NEBA 9, and NEBA 9 will try to load, want to load the kernel. Actually, it doesn't have itself the code to do it, so it will relies on an API that is exposed by Secure Microboot, like a DL open to be very quick. And Secure Microboot will do all the checks and integrity verifications on behalf of NEBA 9. And if everything is good, NEBA 9 will simply jump to iLO 5 kernel. And that's where things got quite interesting. In iLO 5 kernel, iLO 5 kernel is responsible, of course, for checking the integrity of all the iLO userland. Well, where everything is running, like SSH server, HTTP server, everything. What was interesting is that almost we can, in iLO 5 kernel, we can find almost the exact same code for loading modules and checking integrity, almost. iLO 5 kernel will only consider one single key one single public key to check, to decrypt the signatures, and it is called the legacy key. And that's where the 2 index fields we discovered sooner becomes really interesting. So in iLO 5 kernel, there is a function that we called log signatures that is supposed to decrypt the signature fields and pass it for verification. And inside this function, we have one function that is called load legacy key that will use the index we can find in the header. But this function can fail, for example, if you pass an invalid index value. And what is very interesting is that if load legacy key fails for the index 2, it will return with a success code. We suppose that the developer made the assumption that if load legacy key failed for index 2, it means that index 1 has been successful, but it's not the case actually. Both can fail, and that's exactly what we will exploit to bypass the secure boot. And actually, if we do that, the 2 signature fields will be left untouched, and the iLO 5 kernel will simply compare the hash value it has computed dynamically with an untouched field that we can modify as we want. So what we can do is very simple, a bit like what we did with iLO 4. We will simply extract the firmware, get iLO 5 userland, decompress and insert any backdoor we want is in it, recompress. We set the 2 index field to rogue value, invalid values, anything different than 1 actually. And then we will update all size and CRCs, of course, compute the cryptographic hash of the role, and simply replace the signature with the value of this hash. And we can use the CVE Fabien just presented to bypass the Fume integrity check to push it into the flash memory and reboot the server. It was almost perfect, but it didn't work. we screwed up a little. And the situation we were in, we had only a blinking motherboard. iLO services seems started but quite unresponsive and broken. The server was not in recovery mode, and we had thus we had no way to push a new firmware to restore clean state. So it was kind of messy, and we needed more information. On iLO 4, we had some serial output directly from the motherboard, so that's why we tried to find the same feature on iLO 5 motherboard. So we started probing on the motherboard with logic analyzers, and we quickly found these very useful pins here, and especially the serial output from the iLO systems. At the same time, we started probing with the flash memory of the iLO, where iLO RAM is stored, to directly be able to write into it and flip some bytes or write anything we want if we want to flash a new firmware directly. So using the serial output directly from the systems, we were able to identify some error code in the kernel and to locate and to understand what we did wrong. Actually, we had flawed backdoored userland. We had a bad decompression code, which introduced a very late error into the ELF parser of the integrity kernel. And but the kernel thought it has been successful in loading the userland, but it was not quite the case. And that's why it didn't pop the recovery FTP server. So we quickly fixed it. We flip a byte within the flash memory to trash integrity. Then iLO kernel will detect this and enter in recovery mode. We're able to push a new clean firmware. And from there, of course, we fixed our code, and we've been able to push backdoor firmware. And we will show you the demo.
Okay, so quick demo. So on the left, you have the serial output. On the upper right, the host operating system, and then the attacker here. So first, if the attacker tried to contact the SSH service, it's a normal SSH running on the HP server. On the Linux, we will try to flash a modified firmware. So here is the exploitation for the vulnerability in the Fume task. Well, if we try to flash the firmware and it's older than the actual version, it tells us it can, but, well, you can just ask him to load and grade and it will flash it without any problem.
And keep that in mind, it will be important for the rest.
So now we flash our firmware containing both the vulnerability in Fume and the vulnerability to bypass the secure boot. Then iLO reboots. It gets an IP address from the HCP, and now if we try to connect to the SSH service, so we change the banner to show that we can backdoor the username.
Yeah, we can backdoor it permanently. That's very important. So yeah, we bypass the secure boot. We reported it, of course, to HPE, which named it a local bypass of security restriction in firmware update. And they released a fix in iLO 37 in the end of October 2018. There is kind of an issue with that because the root of the root of trust is kind of compromised. And when we analyze the updates they released, we found that first and second stage bootloaders have not been modified at all. They're totally unchanged. And we, of course, have legitimately signed vulnerable kernels in the wild that we can use. The fact that iLO still allow firmware downgrade is problematic because we have many scenarios. We can build some Frankenstein firmware with all vulnerable kernel, signed by HPE, of course, or we can simply downgrade the firmware to a version vulnerable. And what we found, or what we observe, actually, they don't use any means, like hardware means, to revoke the signature of these compromised, vulnerable, kernels, like hardware fuse or things like that. With iLO 5 version 1.39, they actually introduced an anti-downgrade feature, new policy settings that you can enable using the web interface. but it's still a software fix in the update code that will check the version to be sure that you don't downgrade the firmware. We think it's status bit that is stored into the EEPROM. You have no way to from an interface to disable it once you have enabled it, but still it's some software fix. And if you have physical access to the flash memory, or if you can use vulnerability to directly talk to the SPI service and write your own firmware into the flash, you can still bypass the secure boot. So to conclude all this study, we have been able to discover many vulnerabilities that allowed us to really explore all the systems and understand what are the capabilities it offers, especially with its dedicated hardware, like the DMA access to the host and bidirectional channels that can be built upon that. That was very interesting to understand the security model and the threats that pose this kind of feature inside the network. From there, we've been able to summarize all our discovery. We've built some kind of small kill chain from a LAN. An attacker can perform some network reconnaissance, try to discover some exposed iLO systems. We have some X endpoints on the web server that leak lots of memory, the XML data endpoints. Otherwise, you can do simple banner grabbing. And if your, for example, web server is still vulnerable to the vulnerability represented at the beginning of the talk, it can attack your server from it, and then use the DMA feature to pivot to other hosts. From a production network, also, if an attacker is able to compromise, let's say, an exposed services, like an exposed web server, database, or anything, and can access the host from there, then it can access the iLO, from there, then it can pivot through the iLO, and, for example, to pivot through an administration domain, and to attack other servers that will not have been reachable from it otherwise. iLO 5, we have a kind of the same issue, of course. If from production network, we have the same issue, and of course, we still have the issue that the secure boot cannot be trusted at that point. So no more from a system point of view. iLO have a very large attack surface, exposed both on the administration and production network, so it's very important. Unpatched systems will really be a mess. It will be a dreamland for lateral movement, really. Network isolation and segregation is a must, but as we saw, it may be not enough because we can build some channel through the iLO. So it's really critical to keep the systems up to date as soon as possible and to monitor them, of course. iLO 5, basically it's almost quite the same as iLO 4 actually. The system has not changed more. But of course we have interesting hardening feature like security mods, and also the silicon root of trust should have been a killer feature for HPE and for these servers, but clearly actually the implementation is totally hindered by the flood implementation. The feature is totally hindered by that. As soon as there is no hardware provocation with some kind of fuse, they are vulnerable, and the secure boot cannot be trusted. Just a few conclusions also for red teamers. We believe it's a great exercise to play with your blue team. BMC systems are often found unpatched or loosely monitored in a network, and they can open attack paths to otherwise secure systems like we show. And of course also we can achieve persistence even in case of system reincarnation, even if you remove and change the hard drive. We have published an extensive toolkit that you can use to build your own attack vector and backdoor and to pivot through it. And yeah, it's a great exercise to play with the blue team to cover some monitoring blind spot possibly, and to provide, of course, an incentive to patch to demonstrate the need, and to more generally raise awareness around the BMCs. So just as the final words, we'd like to thank many people. First of all, HPE P30 teams, which we have been working a lot since the previous year, and especially Mark and Scott, our friends, Xavier, Raphael, Phil, Adrien, of course, which we did a great job working on the NotPetya things, and our teams for helping us releasing these slides. As we said many times, we have all the tools we developed, script and things like that are on the GitHub. You can check it. And thank you for your attention. And if you have any questions, we're ready for it.
Who wants to ask a question?
Everyone is hungry.